Hello there, and welcome back to the Sleep Science. You're sitting in a place so dark it presses on your skin like velvet. No hum of electronics, no blinking router lights, just the pulse of your own breath against silence. Somewhere nearby, a fire crackles, not your fire, of course. This one belongs to someone much, much older. They huddle next to it, wide-eyed, watching the flames as though they've just met a god. The flickering glow dances over the damp stone walls of their cave. The shadows it casts are enormous, twitching monsters that vanish the moment you look directly at them. And right then, right there, you're watching the first human minds reckon with light and shadow. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tell me in the comments, what's your location and local time right now? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You reach forward in the smoky dark, not to touch the fire but the edges of its glow. You're no inventor, no engineer, not yet, but your eyes are learning something the rest of your brain hasn't quite caught up with. The warmth feels like magic, sure, but it's what happens when your hand drifts into the shadows that makes your stomach twist. Suddenly, it's not just the light that's mysterious, it's the darkness around it. A duality is born. Where there's fire, there's shadow. And that realization might just be the first scientific observation in history. Some archaeologists believe that early humans understood more about fire than we usually give them credit for. After all, it's one thing to keep a fire going, it's another to start one. The presence of scorch marks on ancient hearths suggests that people return to the same places again and again, tending coals, building fuel strategies, even experimenting with materials. Birch bark, resin-rich pine, and dried dung. Fire became more than a survival tool. It was the centerpiece of thought, conversation, and myth. Historians still argue whether early hominins discovered fire from natural wildfires or learned to control it independently. Either way, fire marked a turning point. And with fire came light, flickering, yellow-orange, unpredictable light. You lean in. You can almost hear the hush that falls when the first storyteller lifts their hand, letting it cast a shadow on the cave wall. Suddenly, the silhouette of a bear dances across the stone. The youngest child gasps. Someone makes a low sound in their throat, amusement, awe, or just that familiar flicker of fear that comes when you realize you can see something that isn't there. A bear made of fingers. Magic. These playful shadows, these crude puppet shows, weren't just entertainment. They were early models of representation, art, maybe even early experimentation. What happens if I move my hand closer to the flame? What if I wiggle my fingers? What if I hold a bone in front of the light? A spear? A leaf? Each discovery invites more. Firelight isn't just illumination, it's a whole new language for manipulating the world. There's something deeply funny about imagining a prehistoric inventor accidentally creating the first cinematic experience and being interrupted by a bored toddler chucking a rock into the fire. Popcorn not included. Meanwhile, outside the cave, the sun rises and sets with cosmic disinterest, and humans begin to notice patterns in that too. But for now, you're staying close to the fire because the shadows it casts are tricksters. They stretch when they shouldn't, vanish when you move, split into weird pieces when two flames flicker together. If you're lucky, someone in your little group is already sketching on the cave walls, not animals this time, but repeating patterns of lines and dots. Maybe it's art. Maybe it's math. Maybe it's the earliest attempt to count firelight flickers. Here's your quirky detail for the night. Some researchers believe the shimmer of firelight on cave paintings wasn't an accident. The art may have been meant to be viewed in that flickering glow, creating a kind of animated effect. Buffaloes that seem to move, horses that gallop when you shift the torch. So, yeah, if you ever felt like your wall art was better with mood lighting, Turns out Paleolithic humans beat you to it by about 30,000 years. You're starting to understand something important now. In a world without electricity, light isn't a given. It's precious, rare, and always dying. Every flicker of flame is temporary. This makes it sacred and terrifying. That explains the reverence, the stories, the fire gods and sun deities that show up in nearly every culture's earliest mythology. But it also explains the scientific hunger, because once you've seen light, you want to understand it. You want to know what it is, where it goes when it's gone, why it makes shadows behave so strangely. You want to know how to make more of it and how to keep it burning. Historians still debate the timeline of controlled fire use. Some sites in South Africa show possible evidence going back over 1 million years, while others argue that sustained, intentional fire-making didn't really start until around 400,000 years ago. Either way, it's humbling to think that something as simple as light, a candle, a campfire, a flashlight app on your phone, traces back to this murky, mythic moment. One where a small group of people huddled in a cave, staring into flame, unknowingly launching the entire human relationship with science. The fire's burning low now. One of the elders adds more wood carefully with practiced hands. You watch the light rebound, crawling across the stone ceiling, chasing the shadows back into the corners. Someone nearby yawns. You do too. Light and sleep, another connection. That firelight has begun to train your brain to feel drowsy at night. Melatonin suppression, circadian rhythm entrainment, concepts for future scientists. But even now, your body's learning them, hour by hour. The shadows on the wall shift again. You think they look like animals this time, or maybe stars, or maybe just the restless imagination of someone sitting in the oldest classroom in the world. A ring of stone, a crackling fire, and the endless night beyond it. You're standing now in the searing heat of midday, somewhere in ancient Egypt. The air is dry enough to chafe your skin, and the brightness is almost hostile, a white-gold assault pouring straight from the sun overhead. Your sandals crunch against sun-baked stones as you follow a figure robed in linen. They walk with purpose, stopping before a tall obelisk casting a short, sharp shadow. The man squints up at the sun, down at the shadow, then scratches something into a wax tablet. Welcome to the original sundial. The original attempt to wrangle light into something predictable. At this point in human history, the light isn't just worshipped, it's being measured. And Egypt, with its cloudless skies and near-perfect flatlands, becomes an ideal laboratory. You watch as priests and astronomer scribes begin treating shadows not as magical tricks, but as tools. The length of an obelisk's shadow at noon helps them chart solstices. The angles tell them when to plant grain, when the Nile will flood, when to honor gods and embalm kings. It's a level of precision you didn't expect from a civilization that built pyramids with no backlit calculators. Yet here they are, teasing patterns from the sun's position, jotting down shadow lengths, and slowly, carefully, building the first calendars. There's a brilliance in their simplicity. A stick in the sand, a human figure, a notch in a temple wall. Each becomes a timestamp etched by the sky itself. Historians still argue whether the ancient Egyptians developed their timekeeping systems independently or inherited techniques from earlier Mesopotamian cultures. Either way, they mastered light as a measuring stick. You feel a weird respect for the way they made the sky part of their architecture. Temples aligned to solar events, columns casting shadows that formed hieroglyphs on solstice mornings. They weren't just reading time, they were choreographing it. Here's the quirky bit. To create some of these effects, the architects had to know how light would behave centuries into the future. That's right. Some temples were designed so that a particular room or statue would light up for just a few minutes once a year, during a specific festival or astronomical alignment. It's like building a clock with stone and waiting generations to see if it chimes. You wander deeper into a temple now, away from the blaze. The walls swallow you into darkness, cool and quiet. Your footsteps echo. But look, tiny slits high in the stone funnel daylight down in precise lines like optical syringes. Even inside sacred spaces, light is being bent, sculpted, and directed with purpose. It's used not just to illuminate, but to emphasize, drawing your gaze to inscriptions, to statues, to that gold leaf scarab glinting faintly in the gloom. And then there's the noon trick. You're brought back outside again, this time with a different robed scholar. He shows you two vertical rods, one in Alexandria, the other, you're told, far to the south in Scene, modern-day Aswan. At noon on the summer solstice, the scholar observes something strange. In Scene, the sun is directly overhead and casts no shadow. But in Alexandria, the same vertical rod does cast a shadow. That difference. It's all it takes for a clever man named Eratosthenes to estimate the circumference of the Earth. With no modern tools, no satellites, and definitely no coffee, Eratosthenes uses shadow angles and a little geometry to get astonishingly close to the real number. The story goes that he calculates Earth's girth to within about 1% of modern estimates, though historians still argue over exactly how accurate he was, and whether he made a few lucky assumptions along the way. Either way, the result is jaw-dropping. You watch him scribble calculations in the dust, using nothing more than shadows and sunlight to measure a planet. It's the scientific method, observation, hypothesis, testing, in its earliest and purest form. You shield your eyes now, watching workers erect another obelisk under that cruel Egyptian sun. These stone pillars weren't just for decoration or divine vanity. They were light instruments. Their shadows helped keep track of time, but they also served symbolic functions, linking pharaohs to the sun god Ra, casting divine order over the land, aligning mortal rule with cosmic precision. And yet, there's something deeply human about it all. The man nearest you wipes sweat from his brow, glances at the shadow, and mutters, "It's too short. It's nearly time to break." Even today, somewhere in the back of your mind, you still check your shadow when you need to know how long you've been outside. The Egyptian day was divided differently than ours, with 12 hours of daylight and 12 hours of darkness regardless of the season. Their hours shifted in length depending on the time of year. That meant the pace of life changed with the light. Longer summer hours meant more work, shorter winter hours, more rest. Imagine your boss today telling you, "Oh, your shift's shorter because the sun's lazy." Now that's a time system you could get behind. Somewhere a priest chants, standing beside a sacred lake that reflects the blinding sky. You realize now that light wasn't just a measuring stick, it was a messenger. It carried signs from the gods, omens in eclipses and refractions, answers in the way a shaft of sunlight pierced the dark chamber of a tomb. Light meant something, and if you understood its language, you could read the will of the universe. You squint up at the sun again, thinking back to that noonday observation, how something so simple as a shadow could stretch into science, cosmology, and architecture, and also a little bit of sass. Because let's be honest, Eratosthenes really did look at a stick's shadow and say, "Hold my beer, I'm gonna measure the planet." The obelisk casts its own shadow now, inching forward across the stone like a slow whisper. You follow it with your eyes, knowing full well that thousands of years ago, someone else was doing the same, sketching theories into wet clay, timing prayers to the crawl of that same line. You don't need a smartwatch here. Just the sun, some stone, and the deep, slow patience of people who understood that science begins when you look up and start to wonder. You're standing now in the white marble courtyards of ancient Greece, somewhere between the aroma of olive oil and the soft groan of sandals on polished stone. The sun is bright again, as it always seems to be in this part of the ancient world, but it's not the brightness that holds your attention. It's the strange stillness of minds at work, Around you, philosophers are gathered, draped in robes that somehow manage to look both scholarly and impractical. They speak in measured tones, tracing arguments with styluses on wax tablets, pausing to admire the geometry of shadows cast by their own fingers. Welcome to the birthplace of overthinking. And tonight, you'll be dipping your toes into a very old and very spirited Greek debate. What exactly is light? You ease into a conversation between two thinkers packing under an open colonnade. One is convinced light travels from your eyes like a kind of invisible laser beam, actively reaching out to feel the world around you. Yes, according to this model, your eyes are not passive receivers, they're searchlights, like little flashlights built into your face. The other philosopher shakes his head and suggests that light comes into the eyes from outside, as a substance that needs to strike the eye before vision is possible. This, to be clear, is where people start lightly insulting each other in Greek. Historians still argue whether these early optical theories were genuine stabs at scientific truth or just exercises in rhetorical showmanship. Either way, the Greeks made real contributions, particularly figures like Empedocles and Euclid, who puzzled through the physics of reflection and angles like curious kids with a pocket mirror. You settle beside a thinker drawing lines across the sand. He's experimenting with straight paths. He notices that shadows and beams of light seem to follow linear routes, unless reflected. That leads to one of the earliest documented optical laws. The angle of incidence equals the angle of reflection. Euclid jots that down like it's obvious, which is impressive considering he's working without lasers or lenses, just lamps and cleverness. And then there's Pythagoras. You may know him from right triangles and long-suffering geometry students, but tonight he's caught up in light. He's in the I-beams camp, the idea that vision works because light shoots out of your pupils, hits an object and bounces back. If that sounds backwards to you, you're not alone, but keep in mind this was a time when dissection was taboo and no one had invented the microscope. They couldn't even agree on what an eye was, let alone how it functioned. Still, even incorrect models can lead to correct insights. The Greeks start poking holes in each other's theories, and in doing so, they start refining the language of light. Geometry becomes a crucial tool, not just for land measurement or temple design, but for understanding how light reflects and refracts. Mirrors are suddenly more than vanity tools, they're experimental equipment. A bronze plate polished to a shine becomes a portal into physics. Here's your quirky bit. Ancient Greek temples often used small reflecting dishes to bounce sunlight into dark inner sanctuaries. So yes, they were basically installing early lighting systems, just without wires or switches. And perhaps even more delightful, some scholars argue they used mirrors in religious rituals to make statues appear as if they were glowing or even coming alive, with sunlight at the right moment of day. It's sacred theater, fueled by physics. One of the most mesmerizing thinkers in this chapter is Plato. He believes vision is an interaction between light that emanates from the eyes and light from external sources. To him, seeing is a kind of cosmic handshake between soul and world. Not terribly scientific by modern standards, but it captures something poetic, the sense that vision is more than just photons hitting retinas. It's perception, it's meaning, it's connection. Plato's student Aristotle, predictably, disagrees. He leans toward a more external model. Vision occurs because the object impresses a form upon a transparent medium, the air or ether, which then travels to the eye. That sounds suspiciously like a very early stab at wave theory. Not bad for a guy who still thought the heart did most of the thinking. You look around and realize how seriously these debates are taken. Light isn't just illumination here, it's symbolic. It's tied to knowledge, to clarity, to the divine. To see the light becomes a philosophical awakening. That metaphor still lingers in your language today, thousands of years later. You see it in phrases like enlightenment, shedding light on a topic, or a bright idea. All leftovers from the Greeks' obsession with understanding visibility as the gateway to truth. Now here comes your historical zinger for the night. Pythagoras also believed that light had weight. Some say he thought it consisted of tiny particles, a surprisingly prescient idea that would resurface much later in quantum physics. Of course, he also thought beings contained souls and should be avoided, so maybe take that with a sprinkle of sea salt. You trace the sand where a young student sketches a light beam bouncing off water. She tilts her head, thinking, maybe she'll become the next great thinker, maybe she'll be forgotten. But her curiosity is the same one that's echoed across the centuries. How does light work? Why do shadows bend near water? Why does the sun feel hot, but moonlight does not? And what is it about flame, glow, glare, and shimmer that seems to touch something deep and ancient inside you? Historians are still divided on whether the Greeks ever fully separated science from philosophy. For many, asking what light is was the same as asking what truth or beauty or justice meant. You realize how intimate these ideas are. Light isn't just physics. It's everything: sight, safety, time, art, memory. Without it, the world becomes a guess. As the sun dips low behind the Athenian hills, a soft golden light pours through the columns. Shadows stretch long across the agora. The philosophers don't stop talking. They're arguing about something now, whether fire has substance or is just motion. You back away slowly, letting their voices become background noise. That warm light settles on your face, and for a moment, you understand what they were chasing. Not just clarity, but the mystery hiding just behind it. Because even here, under one of the most rational skis in history, the glow of knowledge never quite burns away the shadow of the unknown. Now you're blinking into the pinkish haze of dawn somewhere far to the east. You've left the Mediterranean behind, and with it, the murmuring philosophers and their sun-drenched debates. Instead, you're perched on the edge of an ancient Chinese observatory, watching the horizon with a team of astronomers who wear silk robes and expressions far too serious for this early in the morning. The air smells faintly of ink, smoke, and jasmine, and the sky is turning that unmistakable gold gray that means something important is about to happen. You just don't know what. And neither, frankly, do they, because today might be the day the sun disappears. You squint. For now, it's climbing steadily upward, radiating warmth across the tiled roofs of Chang'an. But these ancient scientists, some of whom are barely out of childhood, are reading scrolls, consulting bamboo strips, and glancing nervously at polished bronze discs. Why? Because their calculations say there might be a solar eclipse. And in a culture where celestial events were believed to reflect the will of heaven, the stakes are high. Miss it, and you might not just lose your job, you might lose your head. Solar eclipses have long been nature's most dramatic light tricks, and ancient Chinese scholars were among the first to document them systematically. They tracked them, predicted them, feared them. The idea wasn't just scientific, it was political. A sudden vanishing of the sun could mean heaven's disapproval of the emperor. That's not a metaphor. That's grounds for royal panic. You flinch a little as someone nearby bangs a gong, not out of alarm but tradition. They believe a celestial dragon might be trying to swallow the sun, and the best way to save it is by making a terrible racket. You glance up. Sure enough, the sunlight wavers, dims, turns a strange silvery gray. A hush falls over the entire courtyard. The dragon is here. Now, whether anyone actually thought a literal dragon was chewing on the solar disk is up for debate. Historians still argue whether ancient eclipse rituals were symbolic performances or rooted in genuine cosmological belief. Either way, you're watching something that transcends folklore. Because even as villagers bang pots and priests chant to drive away the beast, the royal astronomers are scribbling data. They're measuring light levels, comparing shadow angles, and recording the entire sequence with a rigor that would make any modern lab proud. This moment matters. It's one of the first documented instances where light and its absence are not just feared, but studied. Here's a quirky detail to enjoy while the sun slowly returns to full strength. In 2136 BCE, during the reign of Emperor Zhang Kang, two royal astronomers, HSI and Ho, failed to predict a solar eclipse. They were promptly executed. Brutal, yes, but it speaks volumes about how deeply these early societies tied science to survival. If you couldn't track the light, you didn't just lose prestige, you endangered the empire. You follow the scholars as they retreat into a study hall, heads bowed under the weight of freshly recorded celestial data. Inside, shelves are filled with star maps, eclipse tables, and something you might not expect, shadow-casting instruments. Gnomons, sundials, and calibrated sticks arranged to catch the sun's rays with exacting precision. These were light's earliest rulers. The Chinese gnomon, a vertical rod used to cast a measurable shadow, allowed early astronomers to track solstices and equinoxes, estimate the Earth's tilt, and refine their calendar with astonishing accuracy. And these measurements weren't theoretical. They determined harvest times, tax collection, military campaigns. You realize now, light was governance. Understanding its patterns meant control over both time and society. You pause to look over a parchment filled with arcane symbols. It's not Greek geometry or poetic speculation. It's tight, organized, and practical. The ancient Chinese viewed celestial mechanics less as metaphysics and more as public policy. They pioneered observational astronomy while developing detailed almanacs to guide everyday life, from farming to divination. No time for philosophical meandering when the emperor demands a forecast. And yet the mystery was never entirely lost. Even as the science of light advanced, its spiritual dimensions remained intact. You're told that mirrors here aren't just tools, they're protective talismans. Some are crafted from polished bronze so finely worked they can reflect sunlight onto a distant wall, projecting patterns carved into their backs. Magic? Maybe. Optics? Definitely. The magic mirror phenomenon still puzzles people today. Historians debate whether it was an accidental artifact of casting or a deliberate optical effect. Either way, it's further proof that ancient people didn't just observe light, they played with it. You step outside again as evening falls. In the courtyard, scholars point to the sky, now soft with stars. They don't see chaos in the constellations. They see an ordered script, one they're slowly learning to read. They've begun to understand something most cultures will take centuries to articulate. The idea that light from faraway stars isn't just pretty, it's information. It tells you where you are, how the heavens move, and, if you're very clever, how to predict when a cosmic shadow will fall across your world. It hits you, just for a moment, how terrifying an eclipse must have been for someone without context. The sudden dimming, the eerie cold, the sun vanishing midday like a divine eye blinking shut. No wonder people screamed. No wonder they chanted, wept, prayed, or fought each other in panic. And no wonder the first to demystify it were treated like both heroes and high-risk liabilities. If you could predict the sky, you were either a genius or a danger. Back in the observatory, a candle is lit, flickering softly against polished stone. You sit with a scholar who grins quietly while showing you a page full of circular calculations. He's just figured out how long a year really is, 365, 25 days. The fraction matters. That 0.25 will eventually give rise to leap years, solar calendars, and corrections we're still making today. The candlelight throws soft shadows on the wall behind you, not as dramatic as a solar eclipse, but in its own way just as significant. Because for all their grand theories and dragon-slaying rituals, these scholars have built something lasting, a habit of observation, a reverence for light not as divine but as knowable, something that bends, recurs, behaves, and sometimes, if you're clever enough, tells you what's coming next. The scent of cardamom and smoke drifts through the air as you find yourself in the golden glow of Baghdad during its most brilliant age. It's the early 11th century, and the House of Wisdom, yes, that's what they actually called it, is bustling. Scrolls are being copied, stars are being charted, and the light of knowledge feels as tangible as the sun streaming through arched windows. You duck under a hanging lamp and join a small group huddled around an experiment. One man at the center squints thoughtfully at a glass flask half filled with water. He's not a magician, he's a scientist. His name is Ibn Alhazen, and he's about to change the way the world sees, literally. You might know him by the Latinized version, Alhazen, if you've bumped into him in a dusty textbook. But here, right now, he's just the guy packing around a room with a candle, a screen, and a burning question. How does light travel? Up to this point, people have clung to the old I-beam theory, that somehow your eyes reach out and grab the world with invisible tendrils of vision. Sounds very sci-fi, very Jedi. But Ibn Alhazen isn't buying it. He's been watching the way light passes through air, glass, and water, and he suspects the truth is the opposite. Light enters the eyes, not the other way around. So he builds a dark room, pokes a tiny hole in one side, and observes the world projected onto the opposite wall. And just like that, the camera Obscura gets its moment in the scientific spotlight. You crouch beside him as the light from the outside filters through the pinhole, painting an inverted image on the wall, trees, people, movement. It's quiet, eerie, and profound. The idea that light travels in straight lines, that it can be directed and focused, feels less like a theory now and more like something you can reach out and touch. Ibn Alhazen writes it all down. In fact, he writes a lot down. His book of optics will become one of the most influential science texts in history. Historians still argue whether the full impact of Ibn Alhazen's work was recognized in Europe during the Middle Ages or only after Renaissance thinkers rediscovered it. Either way, what's certain is that he introduced something revolutionary to the study of light: controlled experimentation. Instead of just thinking about light, he tested it. He observed, recorded, repeated. It was the beginning of something modern, something you'd recognize as science. You sit quietly as he explains refraction, how light bends when it moves from one medium to another, like from air into water or from air into glass. He uses a basin of water and a stick, showing how the stick looks broken where it enters the surface. You nod. It's the same trick you've seen a million times at swimming pools, but here it's more than a curiosity, it's a clue. It tells him that light isn't just motion, it has behavior, and behavior means rules, which means laws. And that means it can be predicted. Here's your quirky detail for the night. Ibn Alhazen proposed that the atmosphere itself acts like a giant lens. That's why the sun looks larger near the horizon. It's being distorted by refraction through the Earth's air. He didn't have all the math right, but honestly, not bad for a guy working without a telescope, a calculator, or a steady supply of coffee. Light is everywhere in this city. You walk through the markets at dusk, watching oil lamps flicker behind stained glass. Light is being manipulated, not just with lenses, but with color. Artisans know how to tint glass with powdered minerals, how to arrange mosaic tiles so they glitter at sunrise. In their own way, they too are experimenting with optics, turning physics into aesthetics. You duck into a shadowy side room where a student is engraving something onto a brass plate. It's an astrolabe, a kind of analog computer used to measure the altitude of stars and track time using the position of the sun. It relies entirely on light and shadow. These devices are so accurate that sailors will one day use them to cross oceans. But here, they're also used for prayer, helping people determine the precise time of day and direction of Mecca. Light, once again, becomes the keeper of order. You get the sense that Ibn al-Haytham would have fit in well with modern lab researchers. He doubted everything, including his own conclusions. He insisted that no truth should be accepted without repeated testing, which, in a time when many scholars leaned heavily on ancient authority, made him mildly annoying to his peers, but it also made him unforgettable. Historians note that his approach to science, hypothesize, test, revise, wasn't picked up broadly in the West for another few hundred years. He was centuries ahead of his time, scribbling formulas by candlelight while Europe was still arguing about whether the Earth was flat or pear-shaped. And he didn't stop at light. He ventured into mechanics, astronomy, psychology, but optics remained his favorite child. He believed that to understand vision was to understand how humans encounter the world. Light, to him, wasn't just a physical phenomenon. It was a way to bridge perception and reality. That's the sort of philosophical edge modern science often pretends to forget. You look down now at the notes scattered across his table. Some are in Arabic, others copied into Greek and Syriac. Eventually, they'll be translated into Latin, passed through hands in Italy, Spain, France. They'll ignite curiosity in a generation of European scholars who think they're inventing something new. But it all started here, with a dark room and a tiny hole. As night finally settles over Baghdad, the stars blink awake above the rooftops. Someone lights a lamp. The flame shivers, casting a soft glow across a page that simply reads, "Light moves through transparent bodies in straight lines only." A statement so clean, so obvious now, it almost hides how revolutionary it once was. You breathe in the warm air, heavy with ink and oil and promise. The city feels alive with questions, and the shadows dancing on the wall beside you aren't just emptiness. They're data, waiting to be read, waiting to be measured, waiting for the next mind curious enough to chase the light all the way into the unknown. The sun filters through tall, stained glass windows in bursts of color, so vivid they feel painted onto the air itself. You're inside a medieval cathedral now, massive stone columns rising like trees, the silence broken only by distant footsteps and the occasional hiss of candle wax. It's colder here than outside and your breath almost fogs, but the light is warmer than fire. It streams through reds, blues, golds, and greens, pooling on the flagstone floor like melted jewels. You tilt your head. It's beautiful, but also a bit puzzling. Why does colored glass make sunlight look so alive? Welcome to the Gothic era of Europe, where the mysteries of light are once again becoming holy, and where stained glass becomes more than decoration. It becomes theology, storytelling, and yes, a kind of science. You wander slowly through the nave, the windows towering above you like portals. Each panel tells a story of saints, of angels, of dragons, and miracles. But what really holds your gaze is how the light behaves. It's not random. The craftsmen knew what they were doing. They didn't just pour molten sand into pretty shapes. They selected minerals carefully, copper for reds, cobalt for blue, iron for green. And they didn't just let sunlight in. They sculpted it, focused it, filtered it into messages written in photon and pigment. Historians still argue whether these artisans understood the optics behind their masterpieces or simply stumbled into beauty through trial and error. What's clear is that these windows were more than just holy decor. They were early experiments in refraction and transmission. And every time a sunbeam passed through that colored glass, it taught someone something about light, about space, about wonder. In the monasteries, meanwhile, monks copied old texts, many of them translations of Arabic works from thinkers like Ibn al-Haytham. You may remember him, hunched over his dark room in Baghdad. His ideas traveled across cultures and languages, smuggled through Sicily and Spain into the hands of scholars in Paris, Oxford, and Bologna. Through these texts, Europe slowly began to rediscover the science of light, even if it had to be dressed up in theological robes to be taken seriously. You slip into a cloister garden where an elderly monk is squinting at a polished piece of quartz, holding it up to the sun like a prism. He smiles when the colors fracture across his robe. He's not trying to entertain himself. He's trying to understand something divine. Light, after all, is a central metaphor in medieval Christianity. Christ is often described as the light of the world, and heavenly truth is imagined as luminous, perfect, and ever-flowing. To understand light was to peer into the nature of God. And yet they weren't just philosophizing. Some were quietly experimenting. Thinkers like Roger Bacon, yes, a friar in a robe, began asking practical questions. Could lenses help the elderly read scripture? Why does a rainbow always appear opposite the sun? Why does a stick appear bent in water? He starts writing about mirrors, lenses, magnification. The seeds of real optics are being sown again, right here in the quietest corners of Europe. Here's your quirky bit. Some churches were deliberately built with architectural features designed to capture specific solar events. One cathedral in Italy has a tiny hole in the ceiling and a brass line embedded in the floor. At noon on the summer solstice, the sunlight shines directly through the hole and hits the brass line at a specific point. In other words, it's a sundial baked into a cathedral. Faith and physics playing footsie. Meanwhile, outside these holy halls, a new technology is quietly spreading: glassmaking. You pass a workshop where soot and molten sand swirl together into crude cylinders and fragile panes. As glass becomes more available, the possibilities for experimenting with light expand. Transparent lenses are being shaped, however clumsily, into magnifiers. Someone presses a curved lens against the text of a book and the letters grow. Magic? No. Refraction. But in the 13th century, those two things often looked the same. Magnifying glasses begin appearing in monastic libraries and apothecaries. People with failing eyesight can read again. Monks can illuminate manuscripts longer. Scholars begin studying insect wings under lenses. The world is getting bigger and smaller at the same time. It's not quite science as we know it, but it's close. And every flicker of candlelight through those primitive lenses bends reality just a little. You find a traveling merchant bragging about a new invention. Reading stones, he calls them. Convex hunks of polished glass placed directly on the page. They're heavy, crude, and don't have handles. But for the first time, someone with poor vision can read without squinting. The implications are vast. Knowledge becomes more accessible. Scholars can keep working into old age. Observation becomes sharper. Ideas begin to stretch beyond their physical limitations. Historians note that the rise of glassmaking in Venice during this period had unintended consequences that changed the scientific world. More glass meant more experimentation with lenses. More lenses meant better understanding of light. It's a domino effect, and in a few hundred years, those same ideas will lead to telescopes, microscopes, and cameras. All because someone, somewhere, wanted to make a church window shine just a little brighter. But for now, you sit quietly in a pew as the sun angles through the western rose window. The light scatters across your hands in fragmented color. You realize something strange. No one here fully understands what light is. They don't have Newton yet. No wave theory, no particle debates. And yet, they use it, they shape it, they live by it. Even in its mystery, light serves. You close your eyes and feel the warmth on your eyelids. Somewhere behind you, a choir begins to sing. The voices rise, echoing off the stone, mingling with beams of colored light. You realize you're witnessing a very specific kind of science, not the kind done with equations and whiteboards, but the kind done with silence, patience, and awe. The kind that waits for the sun to move an inch and then writes down what it saw. And in that quiet glow, you feel it again. The sense that light is more than a thing. It's a language, a presence, a whisper from the universe that says, look closer. You're hunched awkwardly over a wooden platform now, somewhere in northern Italy, watching a man balance a long brass tube on the edge of a balcony. Below, the streets of Venice shimmer with early morning fog, their cobblestones already echoing with the clatter of carts and the occasional seagull squawk. The man mutters to himself in an accent thick as olive oil, nudging the instrument just slightly upward. His name is Galileo Galilei, and he's about to look at the moon in a way no human has ever done before. You glance sideways at his handmade telescope. It's not much to look at, just a couple of lenses sandwiched inside a leather-wrapped tube, but when Galileo peers through it, the universe opens. He stares, frowns, stares again. Then he laughs quietly and begins to sketch. What he sees on the surface of the moon isn't smooth perfection. It's cratered, jagged, imperfect. This isn't just astronomy, it's an act of defiance. Because up until this very moment, the heavens were supposed to be flawless. That's what Aristotle said anyway. And if the church had a favorite science advisor, it was definitely Aristotle. So when Galileo starts telling people that the moon looks more like a worn-out rock than a divine orb, things start to get tense. Historians still argue whether Galileo fully grasped the political implications of his discoveries when he made them, or if he simply couldn't help but share what he saw. But one thing is certain: the telescope, and the light that passed through it, was about to upend centuries of thought. You lean over the edge of the balcony as he tilts the telescope toward Jupiter next. Within days, he'll spot 4 small moons orbiting the gas giant, now known as the Galilean moons, in case you were wondering how much credit he eventually got. But at the time, this is deeply upsetting, because if those moons orbit Jupiter and not Earth, then maybe not everything in the cosmos revolves around us. He writes everything down, of course. Precise sketches, diagrams, notes about phases, orbits, and shadow angles. He publishes Sidereus Nuncius, the starry messenger, and it spreads fast. In a few months, his reputation skyrockets, and so does the danger. You follow him to a lecture hall where scholars argue over what the telescope even is. Some claim it's an illusion machine. Others insist it's too unreliable for serious science. But Galileo, he doubles down. He refines the instrument, builds better versions, and keeps looking. And every time he peers through that tube, the light coming into his eye carries with it more questions. Is the Earth really the center of the universe? If shadows on the moon move, does that mean it's turning? Could the heavens themselves be changing? You pass a table covered in parchment. Diagrams of lenses litter the surface, concave, convex combinations of both. Galileo didn't invent the telescope, to be clear. That credit goes to Dutch spectacle makers, probably Hans Lippershey. But Galileo took it further, gave it purpose. He realized that by bending and shaping light just right, you could literally pull distant worlds closer. Here's your quirky tidbit for the evening. Galileo didn't just look up, he looked down too. He used his telescope to spy on ships arriving in port long before they reached land. In other words, he used it to corner the market on cargo news and stock speculation. Science and capitalism, already awkwardly holding hands. You sit beside him as he scribbles a letter defending himself against critics who say his discoveries go against Scripture. He argues carefully that the Bible teaches how to go to heaven, not how the heavens go. A bold move, one that will land him in trouble soon enough. Because as his support for the heliocentric model grows, especially the work of Copernicus, the church begins to twitch. The idea that Earth moves around the sun, blasphemous, dangerous, heretical. Still, he can't look away. Through the telescope, he watches Venus go through phases just like the moon, another nail in the coffin for geocentrism. You can almost see the gears turning in his head. Light behaves predictably. Shadows reveal structure. Celestial bodies obey mathematical laws. If you understand light, you understand motion. And if you understand motion, you understand the universe. Galileo starts writing about inertia, acceleration, and gravity. Light becomes a tool not just for vision, but for deduction. The telescope is no longer just a curiosity, it's a weapon, a beam of truth cutting through centuries of tradition. Of course, not everyone is thrilled. You attend a trial of sorts. Galileo, now much older and much grumpier, stands before a tribunal. He's forced to recant his heliocentric beliefs, placed under house arrest, and lives out his days writing in secret. But even in disgrace, he keeps observing, keeps studying light, keeps thinking. Historians still debate whether his infamous phrase, "and yet it moves," was actually whispered under his breath after recanting. It's poetic but possibly apocryphal. Still, it sticks. Because everyone knew Galileo saw what he saw, and the light through that tiny glass tube changed everything. You leave his villa one evening as the sun dips behind the Tuscan hills. You glance up. The moon is just rising, full and brilliant. And for the first time, you don't see a smooth white disk. You see shadows, craters, texture. You see a world. And you understand why that must have terrified people. Because when you stop thinking of light as divine magic and start thinking of it as data, when you realize the shadows on the moon follow the same rules as the shadows in your garden, then the universe stops being symbolic. It becomes real, chartable, knowable, and that's the most frightening thing of all. The telescope rests on its cradle, still and silent, but it's done its work. Light, once the subject of myth and metaphor, is now a mathematical messenger. And Galileo, cranky and brilliant and endlessly stubborn, has helped deliver the message. The earth moves, the heavens aren't perfect, and light tells the truth whether we like it or not. You're tucked into the dusty corner of a student dormitory now, candles flickering weakly as the rain taps against the windows of a boarded-up manor house somewhere in England. The year is 1665, and plague is slinking through the streets outside. Markets have closed, universities have emptied, and a slightly unkempt, wildly introverted young man is sitting alone in his room, holding a prism. His name is Isaac Newton, and he's about to wreck everyone's idea of what color really is. You watch as he draws the curtains tight, leaving just one shaft of sunlight piercing through a hole he's poked in the wood. The beam hits the prism, just a chunk of glass, really, and explodes into a shimmering ribbon on the opposite wall. Red, orange, yellow, green, blue, indigo, violet. A full spectrum. A rainbow conjured indoors, no rain required. And right there in that dim, plague-ridden room, Newton asks himself a question that changes everything. Is white light really pure? You already know the answer now, of course, because you've seen rainbows. But back then, this was heresy in scientific form. The prevailing theory, even from big thinkers like Aristotle and Descartes, was that white light was the most pure, and that color happened because of impurities in the medium it passed through. Clouds, dust, the glass itself. But Newton had a suspicion. What if color wasn't added to light? What if it was already in it? Historians still argue whether Newton truly discovered the spectrum or simply clarified what others had seen and ignored. But there's no denying how methodically he proved it. You crouch beside him as he does something delightfully simple. He puts a second prism in the path of the rainbow. And when that split light passes through the second prism, guess what? It becomes white again. This isn't just pretty, it's science with teeth. By recombining the colors into white light, Newton proves that color isn't something the glass is doing to the light, it's a property of the light itself. He calls them colored rays, and suddenly the idea of light being singular and pure gets tossed out the window. The new model, white light, is a mix, a blend, a chaotic soup of different hues traveling together. The prism just sorts them out. You lean against the fireplace, watching as he scribbles equations and sketches on every available surface, walls included. He's not just thinking about light, he's dreaming in it. He's connecting it to motion, to gravity, to the way apples fall and planets curve. Because Newton isn't compartmentalized. To him, optics, mathematics, and mechanics are all different verses of the same poem. Here's your quirky detail for tonight. Newton was so obsessed with understanding light that at one point he literally stuck a sewing needle into his eye socket, not to blind himself, but to distort his vision and study the effects. You'd think that would have convinced him to take a break, but no. Newton had the energy of someone who'd mainlined curiosity and then forgotten how to sleep. At this point, you may be wondering, what about the wave theory of light? Well, Newton wasn't a fan. He believed that light was made of tiny particles, corpuscles, he called them, that bounced and refracted and traveled in straight lines. It made sense to him, especially in explaining reflection and refraction. The wave idea, championed by people like Christian Huygens, didn't convince him. But the truth, as always, would turn out to be a bit more complicated. Still, Newton's work on light becomes foundational. His book Optics isn't just a summary of findings, it's a manifesto. A sprawling, detailed, occasionally unhinged look at how light bends, splits, travels, and behaves. It includes experiments, diagrams, even philosophical musings. And while his corpuscular theory would eventually fall out of favor, then boomerang back centuries later, looking at you, quantum physics, his practical work on optics remained rock solid. You follow him into a small workroom where a new contraption waits on a wooden bench. It's his own invention, a reflecting telescope. Up until now, telescopes had relied on lenses, which meant they suffered from chromatic aberration, those annoying color fringes around bright objects. Newton solves this by using mirrors instead, bouncing the light rather than bending it. Suddenly, telescopes become sharper, more compact, and way more powerful. The design is still in use today, every time someone points a space telescope into the void. And it wasn't just theory. Newton's telescopes let him see things more clearly than ever before. Light became not just something to study, but a tool for observing the stars, mapping orbits, and confirming planetary motions. It was like unlocking a cheat code to the universe. But here's the catch. Newton also had a weirdly mystical side. Tucked between his scientific papers are pages and pages of biblical prophecies, alchemical symbols, even end-of-the-world predictions based on light cycles and celestial alignments. Historians still debate just how seriously he took those writings, but it's a reminder that even the giants of science didn't always color inside the lines. Even Newton, king of equations and laws, had his shadows. Back in his study, the rainbow on the wall is fading. The sun has moved. Newton doesn't seem to notice. He's busy writing again, lost in numbers and angles and questions. You glance at the prism on the table, now just a piece of cold glass. But earlier today, it was the key to a hidden truth. You step outside into the chilly gray of an English afternoon. The sky is low, sullen, featureless. No rainbow here. But you know now that even this dull light is a chorus of colors, all singing together just beyond your perception. Newton made you see that. He forced the world to recognize that color isn't painted onto objects, it's carved into light itself. And that the everyday, sunlight through a window, shimmer on a soap bubble, glare off a puddle isn't simple at all. It's layered, structured, mathematical, a secret code hiding in plain sight. You can't help but feel a little awestruck, not just by what Newton discovered, but by how he did it, locked away during a plague, armed with a prism, a beam of sunlight, and the kind of stubborn curiosity that refuses to be quarantined. The air smells like varnish and waxed wood now, and you're standing in a candle-lit laboratory cluttered with copper coils, glass tubes, and the faint tang of ozone. This is no longer the age of ancient scrolls and prisms. It's the Enlightenment, and everything around you is humming with the promise of reason. In one corner, a man rubs a rod with a silk cloth and watches it attract tiny scraps of paper. Another stares transfixed at a glowing bulb that looks suspiciously like it wants to explode. And over in the back, a pale-faced student is poking at a frog's leg with a metal wire. Welcome to the birth of electricity, static shocks, and the spark that made science crackle with possibility. You're in the company of tinkerers, philosophers, and mad geniuses tonight. People like Benjamin Franklin, Alessandro Volta, Luigi Galvani, and even the infamous Giovanni Aldini, who really should not be trusted with access to cadavers and a battery. But let's start simple. You reach for a piece of amber and rub it with fur. That's it. That's the oldest trick in the electrical book. Ancient Greeks discovered that this generated a strange, attractive force, though they had no clue it was electricity. The Greek word for amber is electron, by the way. Now you see where this is going. Fast forward to the 18th century, and the experiments get stranger. Franklin flies a kite during a thunderstorm, in what historians still argue was either a groundbreaking demonstration of lightning's electric nature or a deeply reckless attempt to win a Darwin Award before it existed. Either way, it worked. The key sparked, the string conducted, and humanity officially confirmed that the lightning in the sky was the same thing dancing between charged plates in their labs. It's all electricity. And where there's electricity, there's light. But let's be clear. At this point, no one really understands electricity. They know it zaps, glows, and sometimes makes hair stand on end, but it's still more of a party trick than a practical tool. Enter Luigi Galvani, who notices that frog legs twitch when touched with metal. He thinks this is animal electricity, a kind of vital force specific to living things. He's wrong technically, but not in a useless way. His nephew, Aldini, takes this idea and runs with it right to the morgue. Here's your quirky bit. Aldini famously applied electrical currents to the body of a freshly executed criminal in front of an audience in London. The corpse twitched, an eye opened, a hand lifted, briefly, horrifyingly, as if coming back to life. The spectators screamed. Writers took notes. And somewhere in the distance, a young Mary Shelley began imagining a scientist with a god complex and a monster made of dead parts. So yes, the birth of electrical light is tangled up with the birth of Frankenstein. Science and Gothic horror, forever entwined. Meanwhile, across the channel, Volta is quietly horrified by all this necromantic nonsense. He thinks the twitching limbs have nothing to do with animal energy and everything to do with metal and chemistry. So he builds something new, the voltaic pile. It's basically a sandwich of zinc and copper discs with cloth soaked in brine, primitive, clunky, but the first true battery. For the first time in history, humans can generate a steady electric current. Not just sparks, not just charges. A current, and with that, a new world begins to unfold. You're watching all this from the corner of the lab, trying not to get shocked. Wires snake across the floor, and every so often someone gets zapped and swears in 3 languages. But it's worth it, because with current comes glow. Scientists start experimenting with passing electricity through gases. They evacuate glass tubes and zap them with high voltage. And lo and behold, light. Blue, green, purple. Strange, ghostly glows that flicker like spirits caught in a jar. This is how the early versions of neon lights are born. Not neon exactly, not yet, but what we'd now call gas discharge tubes. And the colors, they're not random. Different gases glow differently when excited. Neon gives off red-orange, argon a ghostly blue, krypton a silvery white. It's chemistry and electricity doing a slow-motion dance of energy and photons. You're holding a Crookes tube now, an evacuated glass chamber with a metal electrode at one end. You turn the crank, build up voltage, and suddenly a greenish glow appears at the far end. That's not just any light. That's a beam of electrons slamming into glass. You're looking at cathode rays, and they'll soon lead directly to the discovery of the electron, and to television, X-rays, and the atomic age. But for now, it just looks like magic. Historians often mark this period as the transition from natural philosophy to true experimental science. The language of light is no longer just metaphor or observation. It's mathematical, quantifiable, repeatable, and blindingly dangerous if you don't ground your wires properly. You duck as someone drops a Leyden jar. The crack of static jumps from the floor to the ceiling like a ghost escaping. It's hard not to feel a little awe. Light, for the first time in human history, is no longer tied to flame. No wick, no oil, no combustion. Just energy, clean, strange, invisible, and yet able to illuminate a room, animate a frog, and raise the dead, sort of. People begin to realize that light isn't just a phenomenon. It's a consequence. A byproduct of atoms colliding, fields vibrating, energy moving from one form to another. You glance up at a crude arc lamp, just a carbon rod crackling with brilliant, eye-watering light. It's noisy, unstable, and smells like burning dust. But it's a sign of things to come. The future will not be lit by candles. It will be powered by electrons, tamed and funneled through filaments and circuits and grids. The Enlightenment didn't just bring reason to the world, it brought literal illumination. And in those flickering tubes and sparking wires, people glimpsed a future of glowing cities, pulsing machines, and flickering screens. You step back into the night air, ears still ringing from a static snap. The stars above seem dim compared to what you've just seen inside, but you smile anyway, because for the first time the darkness isn't winning. Light, real, artificial, harnessed, has joined the human toolkit, and it's not going anywhere. You're perched now on the edge of a velvet-draped lecture hall in early 19th century London, a space that smells like candle smoke and nervous perspiration. The audience around you shuffles in their seats, ladies in feathered hats, gentlemen in stiff collars, all waiting for what the pamphlets have promised will be an electrifying display of optical marvels. At the front of the room, a projector hums softly. Not a modern one, mind you. This is a magic lantern, an ornate contraption with a glass lens, a light source, and a mysterious sense of showmanship. The lights dim. The slide clicks into place, and with a flicker, light reveals an image of a ghost. No one screams, but a few guests gasp. That's the power of projected light in this era, not just illumination, but illusion. And behind these illusions, deeper debates rage. Because light, at this moment in scientific history, has slipped out of everyone's grasp again. Not physically, it's still hitting your eyes, casting shadows, but conceptually. Because no one can agree on what exactly light is. You hover behind the curtain as two titans of science circle each other across decades. Isaac Newton, long buried but still looming, with his stubborn belief that light is made of particles. And Thomas Young, a young physician and polymath who's about to make waves, literally. Young sets up a simple experiment. He cuts two tiny slits into a card and shines light through both onto a screen. If Newton's corpuscles were correct, you'd expect to see two bright spots. Instead, you get something bizarre, a pattern of bright and dark bands, interference fringes. The light doesn't just pass through, it interacts, combines, cancels itself out in places. That's a wave behavior. And just like that, Young's double-slit experiment becomes one of the most famous mic drops in the history of physics. Historians still argue whether this single experiment truly dethroned Newton's corpuscular theory overnight. It didn't. Newton had prestige, and ideas don't surrender easily. But it cracked the armor. Light, it seems, could behave like a wave, a ripple in something invisible, which begs the question, a wave in what exactly? Scientists invent a medium to carry it, the luminiferous ether, a magical, undetectable substance that fills all of space like a cosmic gelatin and vibrates to carry light waves across the vacuum. It has no weight, no resistance, no smell, and no direct evidence for existing, but it helps the math work. It becomes the duct tape of 19th century physics, unseen but everywhere. You pace beside Young as he sketches wave interference patterns and mutters about sound and water. He's not wrong. Those phenomena behave similarly. But light still keeps misbehaving. It bends around corners, diffraction. It creates strange rainbows on oil slicks, thin film interference. And it even polarizes, as discovered by Etienne Louis Malus when sunlight bounced off a Parisian window in just the right way to make him stop in his tracks. You flip through the increasingly ornate notebooks of Augustin-Jean Fresnel, who takes Young's ideas and runs with them. He develops a full wave theory of light, complete with dazzling mathematical proofs and beautifully curved glass lenses, Fresnel lenses, that can focus light with incredible efficiency. You might know them from lighthouses, where they turned puny oil flames into blazing beacons that could be seen miles out to sea. This was light as precision-engineered power, crafted from mathematics and glass. Here's your quirky note for the evening. Fresnel's work was so revolutionary, the French Academy of Sciences initially rejected it until they saw the math. The judge assigned to review it was none other than Simeon Denis Poisson, a die-hard Newtonian who tried to poke holes in Fresnel's theory. Instead, Poisson accidentally proved it right by predicting a bright spot in the center of a shadow, a bizarre effect that was then confirmed experimentally. Awkward. Meanwhile, other scientists start teasing out more weirdness. William Herschel discovers infrared light heat rays, he calls them, just beyond the red end of the visible spectrum. Johann Ritter finds ultraviolet on the other side. Suddenly, the rainbow isn't the full picture. It's just a sliver. Most light, it turns out, is invisible, which is rude, honestly, after all this effort to understand it. And yet the implications are massive. Light isn't just something you see anymore. It's part of an electromagnetic continuum, waves of all sizes and energies from radio to gamma. But that realization is still years away. For now, we're still tangled in the question, wave or particle. You listen as scientists debate it like it's a bar fight. Light can bend like a wave but reflect like a particle. It can interfere with itself but also cast sharp shadows. It does both and neither, depending on how you look at it. Nature, apparently, has trust issues. The tension peaks as James Clerk Maxwell enters the scene with his now legendary equations. He unifies electricity and magnetism into one grand electromagnetic theory and shows that light is an electromagnetic wave, rippling electric and magnetic fields moving together through space. His math predicts the speed of light perfectly. Everything clicks for about 20 minutes. Because then someone asks, but if light's a wave, what's waving? And once again, the room goes quiet. The ether was supposed to be the answer, but no one can prove it exists. It becomes the banana peel of 19th century physics. Everyone steps on it eventually. Back in the lantern-lit lecture hall, the demonstration wraps up. A final image, a glowing skeleton, flashes across the screen. The audience gasps again. It's a photograph taken with X-rays, which will soon be discovered thanks to these strange experiments with cathode rays and unseen energies. But that's still in the next chapter. You step outside into the London fog, your head buzzing, because light, which once seemed so simple, a beam, a ray, a flicker, has now exploded into an argument, a phenomenon that refuses to be boxed in. Is it a particle, a wave, a frequency, a field? The answers don't line up neatly, and the deeper you look, the slipperier it gets. But that's the game now, not to simplify light, but to chase it, follow it around corners, split it with prisms, bounce it through slits, and try to make sense of the shadowy dance that happens when you're not watching. You're walking now through the late 19th century, but it feels like the future. Gas lamps hiss on the streets, steam whistles echo in the distance, and every laboratory seems to hum with electricity. The world is lit in flickers, both literal and metaphorical, as science begins to peel back the curtain on invisible forces. You step into a cramped German lab that smells like ozone and anxiety. A man in a stiff-collared coat is fiddling with glass tubes, wires, and a vacuum pump. He doesn't look like someone about to discover anything world-changing, but within minutes, he will make the invisible visible. Wilhelm Röntgen's lab is dim on purpose. He's experimenting with cathode rays like many others at the time, trying to understand how electricity behaves in near-vacuum conditions. But something strange happens tonight. He notices a piece of fluorescent paper sitting far from the glowing tube, beginning to shimmer. There's no direct line of sight. No beam should be reaching it. And yet it glows. A new kind of ray, invisible, penetrating, eerie. Röntgen doesn't know what it is, so he calls it simply X-rays. You pause as he places his wife's hand between the ray source and a photographic plate. After several minutes of exposure, the result is stunning and a bit horrifying. Bones, a wedding ring, tendons in smoky contrast. It's the first photographic evidence that light, or at least something like light, can pass through flesh and show what's inside. You're witnessing not just a discovery, but the birth of medical imaging. Hospitals will never be the same. Historians still argue whether Röntgen fully grasped the implications of his discovery in that moment, but it didn't take long for the world to catch on. Within a year, X-ray machines appear in clinics. Within 5 years, they're in shoe stores. Yes, really quirky fact alert. Parents could see whether their children's feet truly fit their shoes. It was part convenience, part gimmick, part wildly unsafe marketing stunt. You're pretty sure no one was measuring radiation dosages back then. And speaking of radiation, you duck into a Parisian lab now, where the air is heavy with chalk dust and uranium powder. At a cluttered workbench stands Marie Curie, elbow-deep in an experiment that no one quite understands yet. She and her husband, Pierre, are investigating Becquerel rays, those strange emissions from uranium salts that seem to affect photographic plates in total darkness. Something is leaking energy, but it's not heat or light as anyone knows it. The Curies will soon isolate 2 new elements, polonium and radium, and show that they too emit these mysterious rays. And here's the twist: radium glows, literally. You watch as a small vial on Marie's desk emits a soft, ghostly blue light in the dark. It's beautiful and dangerous. No one yet understands the toll it will take. Not the burns, not the fatigue, not the long-term effects. For now, everyone is enchanted. Even Marie herself wears a locket with a speck of glowing radium inside. It's only later that her notebooks, still radioactive, will have to be stored in lead-lined boxes for eternity. But right now, radium is the future. It glows, it pulses, it promises cures and miracles. And unfortunately, marketing teams take that and run with it. You walk past a store selling radium water tonics, radium face creams, radium toothpaste. Yes, someone even made radium cigarettes, because if there's anything that pairs well with radioactive decay, it's tobacco smoke. One of the darkest quirks of this age is the story of the Radium Girls. You find yourself in a small American factory where young women, mostly teens, are painting watch dials with luminous paint made from powdered radium. They lick the brush tips to keep them fine, a method called lip pointing. No one tells them it's dangerous. Why would they? The glow is marketed as healthful. You see them laughing, painting their nails and teeth with the glowing substance, thinking it's harmless fun. But in time, the truth creeps in. Teeth fall out, jaws decay, the glow stays long after the laughter fades. Historians consider their court battle one of the first major labor rights victories related to workplace safety, and one of the first times light, particularly its invisible, dangerous forms, was shown to be both gift and curse. What began as a wonder had turned into a warning. Back in the lab, you watch as Röntgen's X-rays and Curie's radiation start to overlap in curious ways. Scientists begin to realize that light isn't just what we see. It's a whole spectrum, visible and invisible. X-rays on one side, infrared and radio waves on the other. The electromagnetic spectrum is expanding faster than anyone can keep up. You sit in a lecture hall now where physicists try to reconcile these discoveries. Some cling to the wave theory. Others point to the particle-like behavior of radiation. It's still a mess. You might remember Newton's corpuscles, tiny particles of light. Well, oddly enough, those are creeping back into fashion. The photon hasn't been named yet, but it's on the way. And through it all, light becomes more than science. It becomes spectacle. You pass through an exhibition hall at the 1900 Paris World's Fair where radium glows under glass, arc lights blaze like miniature suns, and X-ray booths let guests peek inside their own hands. The world is being illuminated in new and increasingly unnerving ways. And the biggest irony, for all this obsession with light, humanity still doesn't understand it. You can pass it through bone, bottle it in tubes, generate it with sparks, but ask two physicists what light is and you'll get three answers, maybe more if they've had wine. The night falls gently outside the window and you glance up at the stars. You know now that their light, too, contains secrets. The spectrum of starlight holds information about temperature, distance, and chemical makeup, codes waiting to be cracked. And soon, someone will do just that. But for tonight, the glow of the laboratory, the shimmer of radium, and the flicker of X-rays all merge into a strange, beautiful twilight. You've left the age of candles far behind. Light is no longer just seen. It is measured. It is feared. It is power. You're walking alongside a man with wild hair, mismatched socks, and a distant look in his eyes as he strolls the streets of Bern, Switzerland. He's not packing a university hallway or standing in a lab. He's heading to his job at the patent office, where he spends most of his day reviewing designs for mechanical contraptions with moving parts. But his mind isn't on machines. It's on light, on time, on what happens when you chase a beam of light and try to catch it. The man, of course, is Albert Einstein. And this is the moment where physics breaks open and spills into everything. You follow him as he returns home in the evening, notebook stuffed into his coat, equations bubbling in his mind. In 1905, a year that physicists now call his annus mirabilis, or miracle year, Einstein publishes 4 papers that will upend everything. One of them introduces the idea that light isn't just a wave, as everyone's been saying since Maxwell and Young. No, Einstein suggests that light also comes in packets, discrete chunks of energy. He calls them quanta. Later, we'll call them photons. This isn't a casual theory. It's bold, dangerous, and very much not what the academic world wants to hear at the time. For decades, physicists have been building the universe out of smooth, continuous waves. But Einstein says, what if light sometimes acts like a particle? A little grain of energy that hits surfaces, triggers electrons, and refuses to spread out like a wave should. He backs this with the photoelectric effect, an odd behavior where shining light on a metal surface causes it to emit electrons. The catch: it only works if the light has a high enough frequency. Not more brightness, not more intensity, just higher energy per photon. That doesn't make any sense if light is purely a wave, but it fits perfectly if light is made of particles, each carrying a quantized amount of energy. It's a mic drop for physics. And it's what eventually wins Einstein his Nobel Prize. Not relativity, not gravity, not E equals mc2, but this weird little paper about how light kicks electrons off metal. Historians still debate whether Einstein intended to ignite what became quantum theory with that paper, but whether by design or accident, he launched the world straight into the strangest corner of science. Light, our oldest and most beloved subject, was now both a wave and a particle, depending on how you looked at it. You trail him again, this time not through the streets of Bern, but through the fabric of space itself. In another paper that same year, Einstein introduces special relativity. It's here that the speed of light, 299, 792, 458 meters per second, becomes a cosmic speed limit. Nothing can move faster, not even your thoughts about how weird this is. But it's more than just a number. Light becomes the anchor of time itself. In special relativity, time dilates, moves slower for objects traveling near the speed of light. Length contracts. Simultaneity disappears. All of space and time begin to swirl together, and at the center of this new reality is light, constant, unwavering, immune to motion. You sit beside him one evening as he scribbles equations that will become the foundation of general relativity, a theory not just of motion but of gravity itself. In this model, gravity isn't a force, it's the bending of space-time. And what follows that curve perfectly? Light. When light passes near a massive object, say a star, it doesn't go straight, it bends, like water flowing around a stone. Einstein predicts this effect in 1915, and 4 years later, during a solar eclipse, British astronomer Arthur Eddington proves it. He photographs stars near the edge of the sun, normally invisible due to glare, and shows their apparent positions have shifted. The sun's gravity has bent their light. Einstein is suddenly a global celebrity, a physics rock star, because his math did more than predict a bending beam. It rewrote the rules of reality. Here's your quirky detail. When Einstein first heard his bending light prediction had been confirmed, he reportedly shrugged and said, "I knew it was correct." And when someone asked, "But what if the results had been different?" he replied, "Then I would have been sorry for the dear Lord, for the theory is correct." Modesty was never a requirement for genius. Meanwhile, Einstein's particle theory of light, the photon, starts catching on. It's used to explain not just the photoelectric effect, but things like fluorescence, solar panels, and later lasers. Light is now a quantum object, sometimes wave, sometimes particle, and always just a little unpredictable. You walk through labs that hum with early laser experiments. Light is being forced into lockstep now, photons emitted in perfect unison, coherent and focused like a blade. It's light unlike anything nature makes on its own. Scientists are already dreaming about laser beams, medical tools, data transfer, but this is just the first spark. Back in Einstein's time, lasers haven't yet arrived, but the math is ready for them. What's happening now is a philosophical rift. Because if light behaves like both wave and particle, then what is it really? The question spreads outward like ripples. If light can do this, what about electrons? What about matter itself? And so the next chapter of quantum theory begins, not just with photons, but with uncertainty, duality, probability. Light becomes a symbol of science's triumph and its limits. The more clearly you try to define it, the more it slips between categories, like it's waving at you from a place just outside certainty. You step outside one crisp winter evening, as Einstein might have, and look up at the stars. Their light has traveled years, decades, centuries to reach you. Each photon a tiny messenger, carrying not just energy but evidence of distance, composition, and motion. And because of relativity, some of those photons have been bent by galaxies you can't even see. Their paths twisted, their journeys stretched, but somehow they still arrive. It's humbling, isn't it? That's something so familiar, the warmth on your face, the glint off your coffee mug, the beam through your window. is also this elusive, double-natured, space-warped traveler. That the light bouncing off your page is made of particles and waves, born in the hearts of atoms but governed by the shape of time itself. You glance again at Einstein's notes, scattered like breadcrumbs through the 20th century. In them, light is never just illumination. It's the bridge between the small and the vast, the known and the unknowable. It is, perhaps, the closest thing physics has to poetry. You're sitting in a laboratory now that hums with quiet precision, every surface gleaming under sterile fluorescent light. No soot-streaked chalkboards, no bubbling flasks, just lasers. Red, green, infrared, ultraviolet. Beams so thin and focused they don't look real. Like lines someone drew in the air with a ruler and forgot to erase. You're in the post-war era now, the mid-20th century, and light has officially gone from being a philosophical conundrum to the most engineered force in the modern world. You lean in to watch a technician align two mirrors with painstaking care. Between them, a chunk of crystal and a flash tube, both poised for one glorious moment, and then click. A pulse of ruby-red light fires in a perfect pencil-thin beam. It doesn't flicker, it doesn't scatter. It is coherent, monochromatic, and utterly unbothered by the noise of the room around it. The laser has arrived, and it's about to make everything more precise, from brain surgery to barcode scanners. Historians still argue who really invented the laser. Charles Townes laid the foundation with the maser, using microwaves. Theodore Maiman built the first working optical laser in 1960 using a ruby rod. But what matters more is how quickly the technology leapt from theory to reality. Within months of Maiman's first pulse, the possibilities were already spiraling. Communications, medicine, measurement, weaponry. It was light not just controlled, but disciplined. Photons marching in lockstep like a glowing army. You're holding a CD now. It's a dull silver disc, mostly forgotten today, but in your hand it still shimmers faintly with rainbow edges. That rainbow, a laser's handiwork. Compact discs are written and read with focused light, tiny pits etched into plastic, encoded with sound, movies, software, all deciphered by laser beams. Light becomes data, storage, memory. And that's just the beginning. Lasers get shrunk, refined, reworked. By the 1970s and 80s, they're in grocery store scanners, reading every cereal box and soda can like magic. They're in fiber optic cables, whispering phone calls under oceans. They're in DVD players, laser printers, even laser pointers, the kind teachers used to ruin cats forever. Here's your quirky detail for tonight. In the early days, some researchers nicknamed lasers a solution looking for a problem. It sounded cool, sure, but what was it for? Decades later, it turns out the answer was everything. You're standing now in the control room at NASA in the late 1960s. A technician reports that a laser signal has bounced off a reflective panel left on the moon by Apollo 11. That's right, there's a mirror on the moon. You shine a laser from Earth, it reflects back, and you measure the distance with astonishing precision. It's a lunar tape measure made of light. Not only does this confirm Einstein's theories with glorious smugness, it also gives us new ways to track the Earth-Moon relationship, how far it drifts every year. Spoiler, it's about 3.8 centimeters. And speaking of outer space, Hubble. You ease into the seat of a virtual observatory, watching engineers unpack the Hubble Space Telescope in low Earth orbit. Its massive primary mirror gleams like a mechanical eye. Once focused, it begins capturing starlight with breathtaking sensitivity, light that has traveled billions of years just to be caught on a digital sensor. For the first time, humanity sees galaxies forming, stars exploding, even light bending from gravity. The phenomenon Einstein predicted and photographers now chase as gravitational lensing. All of it made visible by an understanding of optics, precision mechanics, and photon detection. And then there's LIGO. You probably didn't expect to find light in the hunt for gravitational waves, but here we are. Two beams of laser light are fired down 4-kilometer tubes in opposite directions. They bounce off mirrors and return. If nothing changes, they cancel each other out. But if a gravitational wave, some ripple in space-time, passes through, the timing shifts ever so slightly. Enough to detect, enough to confirm. You realize that modern physics listens to the universe, using silence and lasers. You walk through a city now and light is everywhere. In street lamps, brake lights, digital clocks, fiber optic cables running beneath your feet. Entire internet backbones rely on pulses of laser light, turning on and off at dizzying speeds, transmitting trillions of bits per second, all invisible, all lightning fast. It's not just that we've tamed light, we've made it fluent in binary. But we're not just looking outward anymore. You're in a clean room where someone in a white suit is etching patterns onto a silicon wafer. Semiconductor chips are built layer by microscopic layer using lasers, some of which use ultraviolet light to draw features smaller than a virus. That tiny piece of glass in your hand, that's a smartphone camera lens. A little marvel of optics, crafted so precisely that even a fingerprint smudge can ruin its function. It hits you then how far we've come from firelight and stained glass. Light is no longer a curiosity, it's infrastructure. We use it to store memories, scan barcodes, weld steel, correct vision, entertain crowds, and communicate across oceans. But more than that, we use it to see, not just what's in front of us, but what's within us and far beyond us. You pause now, letting your mind drift. A red laser pointer dances across a whiteboard in a quiet classroom. Somewhere else, a green laser slices through titanium during surgery. Another fires between satellite relays in orbit. In each case, light moves exactly where it's told, obedient, precise, but also, somehow, still carrying that old, untamed magic. And now you slow down. The hum of technology softens. You step away from the screens, the servers, the glowing panels. Outside, the night has settled. A lamppost hums beside you. You glance up at the stars, most of which are older than light bulbs, older than glass, older than even the idea of light itself. And somewhere up there, photons that left their source before humans had fire are still arriving, quietly. It's comforting, really, that across thousands of years, from campfires to cathode tubes to coherent light beams, humans have always followed the glow. We've built civilizations around it. We've measured our days, lit our temples, projected our fears and our faces into it. We've turned it into art, weapon, medicine, code. And yet, it still mystifies us. The lights inside dim as you sit back in your chair. The humming slows, your breath steadies. You've seen where light has taken us, but there's still more ahead. You're standing now in the blistering desert heat of New Mexico, 1945. The sun has just risen, but already it feels like it's watching you. There's a strange stillness in the air, too quiet, like the earth itself is holding its breath. A white tower stands in the distance, rigid and geometric against the soft hills of sand and sagebrush. Beneath it rests something that's never existed before, the world's first atomic bomb. And in just a few moments, the sky will be filled with a kind of light no human has ever seen, blinding, blooming, and capable of erasing entire cities. You shield your eyes, not that it would help. When the Trinity test detonates, the flash turns night into day, sand into glass, and silence into thunder. It's light, yes, but not the kind you can stare at. It's pure energy born from the splitting of atoms, an exhalation from the very core of matter. This is no longer light as warmth or guidance. This is light as consequence. Historians still argue whether the physicists behind the Manhattan Project fully grasped what they were unleashing. Some did, some didn't. Some claimed surprise, others quoted scripture. Oppenheimer famously muttered, "Now I am become death, the destroyer of worlds," borrowing the line from the Bhagavad Gita, his face already haunted by the glow he helped summon. And just like that, light became a weapon of unimaginable magnitude. You find yourself walking the blackened plain after the test. The ground is cracked, cratered, fused into something called Trinity, a greenish glass made when sand is vaporized and then melts back into itself. You pick up a shard. It glitters innocently in the sun, the color of a wine bottle cool to the touch. But it hums with history. This isn't just glass. This is evidence. That light can kill. That understanding can burn. A few weeks later, the flash comes again, this time over Hiroshima. Then Nagasaki. You don't watch from above. You're in the city streets among the buildings, watching as shadows etch themselves permanently into stone. People turn to silhouettes in an instant. The light was so intense, so fast, that anything in its path cast a shadow burned into the walls, umbra and penumbra drawn not by sunlight, but by thermal radiation and death. It's beautiful in the most horrifying way imaginable. Here's your grim but fascinating tidbit. Some of these shadows are still visible today. On steps, on bridges, in doorways, ghosts not of people but of their outlines. Frozen moments where the light stopped being metaphor and became devastation. These aren't metaphysical shadows, they're chemical. The surfaces behind bodies received more exposure. Those in shadow were partially shielded. Even in destruction, the light obeyed physics perfectly. And still, people look up. You're now standing in a nuclear testing facility in the 1950s, watching film reels of Operation Upshot Knothole. Scientists and soldiers wear protective goggles while mushroom clouds rise like angry gods. The camera shutters click. The Geiger counters chatter. And through it all, the flashes, those impossible flashes, etch themselves into the American subconscious. They show up in cinema, comic books, Cold War propaganda. Light becomes symbolic again, this time not of truth or salvation, but of annihilation. You enter a bunker lined with photographs. Some are aerial views of bomb tests. Others are X-rays of test animals, charred mannequins, and delicate watch dials glowing eerily in the fallout. Light isn't warmth anymore. It's diagnosis. It's exposure. It's measurement and memory and residue. It lingers on everything. And yet, paradoxically, the very same science that gave us the bomb also gave us hope. Nuclear light became medical light. The radiation that destroys cells also treats cancer. X-rays and gamma rays become tools in hospitals and research labs. You walk past machines that scan bones, blast tumors, and help parents hear their unborn children's heartbeats through ultrasound and Doppler. Technologies all touched by wave physics and energy manipulation. You might think light lost its innocence here, and maybe it did. But that's the thing about light. It never promises to be good, only to be what it is, energy, traveling in waves or particles, obeying no morality, only physics. You pass a museum exhibit with photos from the Cold War. A little girl's face illuminated by a TV warning about fallout shelters. A civil defense film showing how to duck and cover under your school desk. Light is fear now. It crawls from the screen. It lives in drills, in sirens, in simulated countdowns. It becomes part of the national psyche, as real and abstract as memory. And yet again, people adapt. They turn the light back on itself. You're now in the control room of a nuclear reactor. Not a bomb this time, but a slow, controlled fission reaction. Uranium rods submerged in water giving off Cherenkov radiation, a bluish glow that looks like something out of science fiction. It's not hot like flame or bright like a bulb. It's cool, unearthly, the visual equivalent of a ghost's breath. Here's your quirky detail. Cherenkov radiation occurs when charged particles move faster than the speed of light in a medium, like water. They're not breaking the universal speed limit. They're just outrunning the local speed limit, like a sonic boom but for light. It's the optical equivalent of a speeding ticket. So even here in the belly of energy production, light remains a paradox. Silent and beautiful in its glow, yet born from splitting atoms, tiny acts of violence that boil water to spin turbines. Your electricity, it turns out, often begins with a chain reaction. Outside the reactor, the sky is perfectly blue, peaceful. The sun is shining, oblivious, but you know better now. You know what light can do, not just in theory, not just in labs, but in the real world. The streets of Hiroshima, the deserts of Nevada, the cores of reactors humming beneath cities. And somehow, amid all that, we keep building. We keep using light, harnessing it, trusting it. Because for all its terror, it also gives us power, progress, healing. That's the shadow of science. Every discovery contains both. Light that can blind can also reveal. Radiation that scars can also cure. You sit for a while at the edge of a testing field. The silence returns. The glassy earth still shimmers faintly under your feet. Somewhere beyond the horizon, the next invention stirs, an idea waiting to catch fire or to contain it. And still, even here, the sun continues to rise. You're beneath the ocean now. Well, not you exactly, but the light. It pulses through a glass strand no wider than a human hair, bouncing between the walls of its sheath like a frantic tourist who refuses to take a direct route. This is fiber optics, and while you're above ground sipping coffee and Googling cat videos, light is sprinting silently below your feet, carrying your messages, your memories, your data. It's the 21st century's circulatory system, and it's glowing. Welcome to the age of information, where photons don't just light your way, they carry your voice, your money, your playlists, your emojis. It all starts with a laser, of course. A precisely tuned one blinking millions, sometimes billions of times per second. Each pulse is a bit off, on, off, on. Over long distances, this blinking laser is aimed into an optical fiber, a thin strand of ultra-pure glass, and from there it zips across cities, countries, even entire oceans. You're walking now through one of the first transatlantic cable stations, somewhere in the cold, gray coastlines of the UK or Canada. The early telegraph wires that once crossed the ocean were metallic, heavy, and frustratingly slow. But now, modern cables are different. Bundles of optical fibers wrapped in steel and waterproof insulation, snaked under the sea like electric eels. Some stretch for thousands of miles. Most people don't even know they exist. But without them, the internet collapses. Here's the quirky part. These fibers don't just carry one stream of light. They carry many. Using a technique called wavelength division multiplexing, engineers can send multiple light signals, each at a slightly different color, down the same fiber without interference. It's like getting a dozen conversations down the same hallway at once, each one in its own pitch. No yelling required. You're in a server room now. Racks of blinking machines, quiet fans, and the occasional operator sipping something caffeinated. Beneath the floor, fiber cables snake like veins. Every email, every live stream, every midnight meme scroll, converted to light, shot through glass, and decoded on the other end faster than you can blink. Literally. Historians still debate whether any single invention, radio, electricity, the transistor, can be called the most important for the modern world. But fiber optics, it's in the top 5 and no one even notices it. It's hidden light, domestic light, tireless and shy. And it's not just data. You're now in an operating room where fiber optic cameras snake inside the body, giving surgeons a real-time look at what's happening inside without needing to make massive incisions. Light doesn't just reveal, it guides. It probes. Endoscopes, laparoscopic tools, and laser scalpels all rely on light in ways that medieval barbers with bone saws could never have imagined. You step into an optical lab next. Here, scientists are pushing boundaries again, working on photonic chips, which use light instead of electricity to move information. These chips run cooler, faster, and potentially more securely than traditional electronics. We're heading into a future where computers may talk to each other not with electrons, but with tiny pulses of laser light. The same technology that once lit up disco balls is now negotiating cryptocurrency. And it gets stranger. Scientists have started creating invisible materials, metamaterials, carefully engineered to guide light around an object, like water flowing around a stone. The result, optical cloaking. In other words, invisibility. It's still crude, still experimental, and mostly only works for certain wavelengths, but it's real. Light, that oldest of elements, is finally being tricked, and we're the tricksters. Back in your home, you're looking around and realizing how much light already governs your world. Motion sensor lights that flick on when you enter a room. Infrared sensors in your TV remote. LiDAR in your robot vacuum, mapping your living room with invisible beams. It's not the future anymore. It's the Tuesday evening version of it. Look up. Satellite communication lasers are being tested now, replacing older radio frequency systems. Lasers don't scatter as easily. They're faster, harder to intercept. Military-grade communication now zipping through clouds with light-speed privacy. You won't see these lasers. You won't even know they're there. But they're humming silently overhead, carrying the negotiations, coordinates, and coordinates of the future. And of course, there's your smartphone. That little dot on the front that flashes when you unlock your phone. That's structured light, a 3D map of your face built from a constellation of invisible beams. Light, again, used not for vision, but for identity. We've come a long way from firelit cave walls and sun-worshipping temples. Now, light builds your relationships, curates your playlists, and navigates your morning commute. Fiber optics didn't just change how we use light. They changed what we think it is. It's no longer an external thing flickering at the edge of the world. It's intimate, immediate. It is, quite literally, part of your daily breath. And it's still changing. You're inside a quantum lab now, where entangled photons are being generated for quantum communication. These aren't beams of light in the normal sense. They're information packets that can't be intercepted or duplicated. Scientists are building networks that use the fundamental weirdness of light to create unhackable encryption. It's light that knows when it's being watched. Yes, really. You watch as a researcher sends a single photon through a beam splitter. It goes both ways, or neither, or both until measured. Quantum weirdness again. But this time it's not abstract. It's a network architecture. The first quantum internet nodes are already online. You just don't notice them yet. And maybe that's the point. Light has gone quiet. It's left the torches and spotlights behind. It no longer needs to announce itself with brilliance. It lives inside machines, inside glass, inside code. It's the backbone of your world now, not just seen but felt. Not just illuminating your way, but becoming your way. So when you pick up your phone or join a video call or stream a movie or text someone across an ocean, remember, that's light moving through the earth. Underwater, underground, underfoot. A photon's journey from one device to another. Soft, instantaneous, invisible, but always there. You're floating now, weightless above the earth, looking down through the faint haze of atmosphere at a planet glittering with light. City grids sparkle like constellations. Lightning forks across distant clouds. Satellites drift silently, blinking as they pass. This isn't a dream, it's a telescope's eye view. You're riding along with the machines we've launched into orbit, each of them built to catch the light that never makes it to the ground. Because here's the thing Earth doesn't tell you, it hides a lot. Our thick, turbulent atmosphere bends, blurs, and absorbs much of the light that comes from space. The twinkle of stars, that's distortion. The soft blue of the sky, that's scattering. You're living under a cozy optical blanket, and for centuries it blocked us from seeing clearly. That all changed the moment we took our telescopes above the clouds. You drift toward a satellite that's changed how humanity sees the universe. Hubble. Launched in 1990, it didn't start off well. Its mirror was ground a few microns too flat, an error so small you could barely see it with the naked eye, but in space it made the stars smear like finger paint. After public embarrassment and a few savage headlines, NASA sent astronauts to fix it. They installed corrective optics. Basically, Hubble got glasses, and the results, breathtaking. You stare at the deep field images, photos taken by pointing the telescope at a seemingly empty patch of sky and just waiting. Days of exposure collecting every stray photon. And the result, not darkness but thousands of galaxies, spirals, ellipses, redshifted smudges from the earliest moments of time, each one pouring out light that began traveling before humans had fire, before Earth had oceans. It's not stargazing, it's time travel. Historians still marvel at how the Hubble Deep Field changed cosmology. Before it, estimates of the number of galaxies ranged wildly. After it, the scale of the universe multiplied tenfold in the minds of the public. Light, once limited to our own sun and stars, was now a flood of ancient messages, finally decipherable. You're watching the spectrum now the way astronomers do. Not just the visible colors, but the spread beyond. Ultraviolet, infrared, X-ray radio. Each part tells a different story. Infrared shows warm dust clouds where stars are forming. Ultraviolet reveals the searing heat of young stars. X-rays map the violent hearts of black holes. Radio waves trace the structure of galaxies. Light is no longer a picture, it's a profile, a fingerprint, a symphony of frequencies revealing structure, motion, even chemical composition. And that's where the James Webb Space Telescope comes in. You float beside it now, its gold-coated hexagonal mirrors gleaming in the sun. It doesn't look like a telescope. It looks like a golden origami flower resting on a sunshield the size of a tennis court. Webb doesn't see what Hubble sees. It looks deeper into the infrared, further back in time. You peer through its lens and see galaxies colliding, stars birthing, planets glowing faintly in other solar systems. This isn't just science, it's cosmic intimacy. You're watching the light of other worlds. Here's your quirky note for tonight. Astronomers using space telescopes can identify elements on planets light years away just by analyzing how light passes through their atmospheres during a transit. They look for dips and wobbles, for the telltale signs of water vapor, methane, carbon dioxide, even potentially life. It's called spectroscopy, and it's basically alien weather forecasting via photon sniffing. Back on Earth, you enter an observatory atop a Chilean mountain where the air is thin, and the stars are so bright they almost hurt your eyes. Massive ground-based telescopes like the Very Large Telescope, no, seriously, that's its name, now use adaptive optics, flexible mirrors that adjust hundreds of times per second to cancel out atmospheric blur. A laser is fired into the sky to create an artificial guide star, letting the system constantly recalibrate. The result: crisp, space-grade images from the ground. Even more impressive, interferometry. Scientists now link multiple telescopes together, sometimes across entire continents, to form a virtual telescope as big as the distance between them. That's how we got the first ever image of a black hole in 2019. Not a simulation, not an artist's impression. A real image created by syncing radio telescopes around the globe, capturing photons warped by gravity itself. Light bends, remember, just like Einstein said. But the space race isn't just about stars and galaxies. You look down at Earth and see satellites monitoring deforestation, weather patterns, ice sheet movement, all through remote sensing, special cameras tuned to reflectance, temperature, chlorophyll content. Light doesn't just teach us about the stars anymore. It teaches us about ourselves. You fly over a city now. Nighttime. The patterns of human activity glow from above. Cars, streetlights, buildings, cell towers. This is artificial light, and from space it's an entirely new form of cartography. You can see development patterns, population density, even blackouts. During conflict or disaster, satellite light maps become vital tools. In the absence of glow, they show suffering. And yet, there's a cost. You glance toward a cluster of observatories in Arizona. The astronomers there are fighting a new battle: light pollution. Even the best telescopes struggle when the sky is washed out by street lamps and advertising. Some scientists push for dark sky reserves, areas where artificial light is minimized to protect our view of the cosmos. Because the more light we create, the harder it becomes to see the light that's already out there. Still, the instruments keep improving. We've launched telescopes that detect gravitational waves, that spot gamma bursts, that image exoplanets. Each one capturing a new kind of light, or light's distant cousins. You begin to wonder if we've reached the end of what light can tell us, but no, we've only just begun. And as you drift away from Earth, you realize something else. That speck of blue below you, it's glowing. The atmosphere reflects and refracts sunlight in stunning patterns. The auroras shimmer with charged particles colliding. And at night, Earth still pulses with light, some natural, some human, all of it telling a story. Light has always been our messenger, from the stars, from our own inventions, and from the planet itself. It tells us who we are, where we're going, and how far we've come. Whether reflected off moons, bent by black holes, or bouncing off a coffee table at home, it whispers the same thing. There is always something more to see. You're knee-deep in the warm, shallow waters of a midnight bay, somewhere in the tropics. The sky above is a dome of stars, but tonight your attention is on the waves below. With each step, the water stirs into streaks of electric blue. You pause, move again, more glowing swirls. Tiny bursts of light ripple away from your ankles like the ocean is alive and excited to see you. And in a way, it is. This is bioluminescence. Light made not by fire or filament, but by living things. Creatures that sparkle, shimmer, flash, and glow for reasons more ancient than memory. Nature, it turns out, is full of light. You crouch and lift a handful of glowing water. It slips through your fingers, trailing flecks of blue-green brilliance. What you're seeing is a reaction called luciferin oxidation, triggered by the enzyme luciferase. Oxygen hits a compound in the organism, and poof, light. No heat, no burn, just cool radiance. This is cold light, efficient, elegant, and far older than any light bulb. Historians can't agree on who first described bioluminescence scientifically. Some point to Aristotle noting the cold fire of certain fish, others to Pliny the Elder writing about glowing wood and jellyfish. Either way, the curiosity has been with us forever. Early sailors wrote about milky seas, vast stretches of glowing ocean visible for miles, thought to be caused by colonies of bioluminescent bacteria. Entire ships sailing through what looked like liquid stars. You reach into a tide pool and spot a comb jelly, its cilia scattering light into rainbows. It's not glowing like the dinoflagellates in the water, it's refracting ambient light. A reminder that nature plays with light in multiple ways, producing it, shaping it, even pretending to be it. You wade deeper. Suddenly, something darts past, fast, sharp, and flickering. A squid. Not just any squid, but one of the deep-sea varieties with photophores along its body, specialized organs that flash like tiny searchlights. Some squids use light for camouflage, matching the faint glow from the surface above to avoid casting a shadow for predators below. Others use it to confuse enemies, attract mates, or even blink in elaborate patterns that resemble underwater Morse code. It's communication, disguise, and art, all written in light. Here's your quirky detail. The Hawaiian bobtail squid has a built-in relationship with bioluminescent bacteria. It hosts them inside a specialized light organ and feeds them sugar. In return, the bacteria emit light to help the squid blend in with moonlit water. It's symbiosis via sparkle. Nature doesn't stop at squid. Fireflies flicker across summer fields, each species with its own timing pattern like a secret code flashing across the dusk. Some males glow in a rhythm designed to woo mates. But there's a dark side. Females of certain species mimic the mating flashes of others, luring males in and then eating them. Love, lies, and murder, all in blinks of yellow-green light. You sit in a forest clearing now, fireflies pulsing in waves. The display is hypnotic. Some regions have synchronous species, whole clouds of fireflies blinking in unison like a slow-motion disco ball. How? Scientists still debate whether it's a neurological trick, a social behavior, or just electrical coincidence. But standing here, you don't care. It's dazzling. Then there's the anglerfish, the deep-sea horror movie icon, that eerie lure swinging from its forehead. It's a glowing organ filled with bacteria dangling in front of a mouth full of needles. The light draws in prey curious fish, crustaceans, right into its maw. Not exactly cozy, but highly effective. Down in the abyss where sunlight never reaches, bioluminescence isn't just a feature, it's a survival strategy, a predator's flashlight, a prey's cloak, a social handshake in the dark. Scientists once assumed that most of the deep ocean was inky and empty. Turns out it's a carnival of light. More than 75% of open ocean creatures produce bioluminescence. Shrimp that spit glowing clouds to escape. Jellyfish that pulse in blue and violet when disturbed. Even sharks, certain deepwater species, glow from belly photophores, possibly for camouflage or communication. Glowing sharks, just what you needed to think about before your next beach trip. You glance up at a canopy where certain fungi glow faintly green. Foxfire, it's called, found in decaying wood. In some cultures, people used it to light paths through forests, calling it fairy fire. Scientists believe it attracts insects to spread spores. So even rot glows. Even death finds a way to light the way forward. And now we're copying them. You're in a biotech lab, watching a gene being spliced into a zebrafish embryo. This gene encodes luciferase, borrowed from a jellyfish, and causes the fish to glow under ultraviolet light. Why? Because now researchers can track gene expression, monitor cancer progression, or test drug effects in real time. Glowing fish, glowing mice, even glowing plants have been made, not for beauty, but for knowledge. Here's the kicker, we've also made glowing beer. Scientists engineered brewers' yeast to glow slightly during fermentation. Practical? Not really. Entertaining? Absolutely. You walk into a nightclub next, not the dancing kind, but a deep tech startup in Singapore that's testing bioluminescent trees as living streetlights. No wiring, no energy bills, just engineered plants glowing softly along sidewalks. It's still experimental, brightness, durability, environmental safety, but the dream is there. An urban landscape lit not by electricity, but by life. And maybe, in some future not far off, your room light won't come from a lamp, but from a vine on the wall. Or your phone screen won't be LED, but organic cells programmed to light up when touched. Or emergency exit signs in tunnels might be glowing fungi genetically tuned to green. It sounds like science fiction, but it's getting closer to science fact. You pause now at the edge of a coral reef. The polyps glow faintly under UV light, revealing patterns invisible by day. Biofluorescence isn't the same as bioluminescence. It doesn't produce light, it transforms it. The coral absorbs ultraviolet rays and re-emits them as visible color. Why? possibly protection, possibly attraction, possibly something else entirely. The debate's ongoing. But here, in this glowing ocean cathedral, it doesn't matter. What matters is that the universe has always known how to play with light, long before humans ever tried. The surface above ripples, your breath is slow. You surface into a night sky freckled with stars and realize the difference between bioluminescence and starlight is only scale, a jellyfish in the dark, a galaxy in the void. Both are stories told in photons. Both are sparks in the great black sea. You're standing at the edge of a chalkboard now. Not just any chalkboard, but one covered in equations so dense they look like some ancient wizard's curse scrawled in Greek and symbols. The room smells of old books and machine oil. There's a soft whir of cooling fans, the glow of a monitor left on standby, and one persistent flicker of fluorescent lighting overhead, as if trying to match the erratic heartbeat of someone about to lose their grip on reality. You're in a quantum physics lab and light, your old friend, is no longer behaving. It's refusing, in fact. You take a breath and peer into the heart of the quantum experiment before you. A beam splitter, a photon source, some carefully aligned mirrors. This is the double-slit experiment again, but quantum style. Instead of millions of photons, just one. A single photon, one at a time, and it still makes an interference pattern. A single particle that acts like a wave, until you try to watch it, that is. Then, poof, no more interference pattern. It's like the photon knows it's being watched. This isn't just odd, it's deeply unsettling. You're seeing quantum superposition in action. The idea that a photon can exist in all possible paths until observed. Light isn't just a wave. It's not just a particle, it's a probability. It exists everywhere it could be, until it decides where it is. Historians of science still argue over how much of this strangeness is philosophical fluff versus fundamental truth. But the experiment is real. It's been repeated, verified, and each time it whispers, reality may not be what you think. You sit now with a physicist who's tired, brilliant, and possibly one cup of coffee away from unraveling. She explains entanglement when two photons are linked, not just in behavior but in fate. Change one and the other changes instantly, even if they're light years apart. Einstein hated this. He called it spooky action at a distance. But experiments have confirmed it, again and again. You're watching light become a carrier of information, not just across space, but across non-locality. Here's your quirky tidbit for the night. The 2022 Nobel Prize in Physics went to 3 scientists who proved that quantum entanglement isn't just a theoretical oddity. It's real, measurable, and fundamentally challenges the idea that particles have properties independent of measurement. Light, in its photon form, isn't just misbehaving. It's redefining what it means to exist. Now you're in a cleanroom lab, thick with the smell of isopropyl alcohol and ambition. On the table, a quantum computer prototype. Not a beige box with blinking lights, but a complex lattice of superconducting circuits chilled to near absolute zero. Inside this machine, photons are being used not to carry information, but to be the information. Qubits, quantum bits, use superposition to be both 1 and 0 at once. Entangled photons maintain correlations that allow for computations no classical computer could manage. This isn't just new tech, it's a new way to think. And quantum optics is leading the charge. Lasers, carefully filtered down to individual photons, are being sent through crystal lattices, where they interact in nonlinear ways, creating new light forms, like squeezed light, where uncertainty is redistributed between a photon's properties in a way that defies classical limits. It's like squeezing a balloon. Make one part smaller, another bulges. Except the balloon is probability, and you're squeezing reality. You blink, it's a lot. Now let's add another layer, time. You're watching an experiment where light is used to observe electron movement, not just in space, but in time. Using a Toscan pulses, 1/quintillionth of a second, scientists can now freeze-frame the movement of electrons around atoms. It's photography at the edge of existence. Light, moving fast enough to catch things that used to be invisible. It's like trying to film the flap of a hummingbird's wing. But the hummingbird is an electron, and the wing is moving at a fraction of the speed of light. And yes, they've done it. In 2017, researchers captured the moment an electron tunnels through a barrier in a process called quantum tunneling. You're watching the impossible become observable, thanks to light's cooperation. Still with me? You step into a quantum optics conference now. The speakers are arguing politely and with only mild existential dread. One insists light is a field, the other insists it's an event. The third says the distinction doesn't matter because we've never truly seen a photon. We've only ever caught its footprints. And everyone agrees that no one quite agrees on what light is, just what it does. You're now inside an art installation at CERN, where a display recreates wave-function collapse with colored lights that dance as viewers approach. It's beautiful, pointless, necessary. Because in this quantum world, observation isn't passive, it's creative. You, the observer, affect the outcome. It sounds like magic, but it is. It's measurement, and this might be the most disorienting truth of all, that the act of measuring light fundamentally changes it. That reality is not something you merely uncover. It's something you participate in. Light becomes your mirror and your medium, your tool and your trickster. You take a breath, back away from the chalkboard. The equations are still there, looping in spirals of uncertainty and beauty. Somewhere in the math, the photon behaves as both a messenger and a mystery. But even now, centuries after cave fires, after Newton's prisms, after Galileo's telescope, light is refusing to settle. Maybe that's its lesson. That some things resist simplicity. That truth, like light, comes in packets and waves. It hits you in bursts. It scatters. It interferes with itself. It's never quite where you expect. And in that uncertainty, there is possibility. You're standing inside a building that hums with quiet urgency. No signs, no crowds, just air so still it feels pressurized. You pass through security checkpoints, clean corridors, and into the vast, echoing heart of a facility that looks more like a spaceship hangar than a lab. In the center sits a circular chamber the size of a sports arena, cables snaking in every direction, sensors hanging like chandeliers, and a collection of lasers pointed with military precision at a single target. This is where humans are trying to do the impossible. This is where we are trying to recreate the sun. Welcome to a fusion lab. The idea sounds simple. Take two hydrogen nuclei, slam them together, and they merge into one heavier atom, releasing a burst of energy in the process. The same thing our sun has been doing calmly for billions of years. Do that here on Earth, and you have clean, virtually limitless power. No carbon, no long-lived waste. Just the light of a star, bottled in steel and magnets. But simple doesn't mean easy. You glance over the shoulder of a technician, adjusting laser optics at the National Ignition Facility in California. This place fires 192 lasers into a tiny pellet of hydrogen fuel, compressing it to hundreds of billions of atmospheres, hotter than the core of the sun. For a few billionths of a second, it glows with the light of a miniature star. Just a flicker. But that flicker holds more promise than any coal plant ever could. Historians will likely mark this moment, the laser-powered fusion breakthrough of the 2020s, as one of the most ambitious intersections of light and hope in modern science. It's the culmination of decades of theory, countless false starts, and more than a few melted components. And here's your quirky detail. The lasers used at NIF are so powerful, Their total energy exceeds 2 million joules in a single pulse. That's enough to boil a bathtub of water in an instant, but instead, it's all aimed at a capsule the size of a peppercorn. Focused light, coordinated to the nanosecond, attempting to rewrite energy history. But NIF isn't alone. You hop over to Europe, where the ITER reactor in France is being assembled, a fusion tokamak that uses magnetic confinement instead of lasers. Giant coils swirl plasma into a donut-shaped chamber, heating it with radio waves and electric currents until it glows like the surface of a star. It's beautiful and dangerous, and again, full of promise. Here, light isn't just something to admire or analyze, it's something to make, something to engineer. The goal is to generate more energy than it takes to trigger the reaction. Scientists call this ignition. We're not quite there yet, but we're close enough to smell the plasma. You walk the halls of these labs and sense the scale, not just in megawatts and funding, but in ambition. Fusion energy isn't just about power, it's about the future of civilization, a world lit by starlight we create ourselves. Still, even outside the labs, people are tinkering with artificial suns. You step onto the floor of a solar thermal plant, massive mirrors stretching out in precise rows, all angled to reflect sunlight toward a central tower. At the top, salt is melted and stored at searing temperatures. Later, the heat is released to generate steam and drive turbines. A desert filled with lenses, using focused sunlight to power entire cities. And then there's the other kind of artificial sun, one you carry with you every day. You pull a solar panel out of your backpack, lightweight, flexible, efficient. It converts sunlight into electricity using the photovoltaic effect, a discovery made in the 1800s and once considered little more than a curiosity. Now, it's everywhere. Rooftops, street signs, phone chargers. Sunlight transformed into electrons with no moving parts. Silent, clean, and slowly reshaping the global energy market. Solar energy has become the most affordable electricity in human history. In some regions, it beats coal and gas, even without subsidies. That's the power of understanding light, turning photons into fuel, daylight into data. The sun, long worshipped and feared, now works for us. Quietly, reliably. You walk through a village in sub-Saharan Africa where kids do homework under solar-powered LEDs. No grid, no wires, just a panel, a battery, and a bulb. The glow is soft, but the impact is enormous. For millions of people, light is no longer a luxury. It's a guarantee. You duck into a lab again, this time in a startup that's experimenting with perovskite solar cells. Cheaper, easier to manufacture, and potentially more efficient than traditional silicon. They can be printed onto glass, layered into fabrics, even embedded in building materials. Windows that power your home, backpacks that charge your devices, cities that generate electricity from their own surfaces. And yet the goal isn't just more light, it's better light. You're handed a panel coated in a special film that adjusts color temperature based on the time of day, mimicking natural sunlight, encouraging circadian rhythms, reducing eye strain. Lighting, it turns out, can help regulate sleep, boost focus, and even influence mood. Smart bulbs that wake you gently, not with a jolt. Offices that shift from cool to warm hues as the hours pass. It's not just energy, we're engineering experience. Even agriculture joins in. You visit a vertical farm bathed in magenta light, LEDs tuned precisely to the absorption peaks of chlorophyll, more efficient than sunlight. Less water, less space. Year-round strawberries in shipping containers. Photosynthesis redesigned by algorithm. Here, where it all collides, energy, food, architecture, medicine. Light as a multi-tool, as infrastructure, as ecosystem. You step outside, blinking at the real sun. It still rises, still floods the horizon with warmth and brilliance. But now we meet its gaze as peers. We've learned to split light, bend it, trap it, and now mimic it. We're building suns of our own, not for worship, not for fear, but for survival, for comfort, for continuity. And perhaps one day, when fossil fuels are long forgotten, and the cities hum quietly on solar grids and fusion cores, someone will look back and say, "That was the moment we turned toward the light and didn't look away." You're standing at the edge of tomorrow now, somewhere between a research lab, a design studio, and a sci-fi movie set brought to life. The walls around you shift with ambient glow, not from bulbs or fixtures, but from panels woven directly into the fabric of the space. They respond to your presence, softening when you're still, brightening as you move. It's not just lighting anymore. It's light as architecture, as interface, as intent. This is where light lives in the future, not as a passive feature, but as an active participant in your environment. You walk across a floor made of photovoltaic tiles that capture the sunlight from the atrium above and use it to power the building's internal network. The walls are embedded with OLED sheets, thin, flexible, responsive. You can paint light now, shape it, layer it like wallpaper, bedrooms that simulate sunrise in winter, workspaces that adjust hue to match your mood, art installations that breathe. You touch the wall and it glows under your fingertips like it's alive. And maybe it is. In this future, light and data have merged completely. You look up, there are no Wi-Fi routers, just panels emitting Li-Fi signals, light-based internet, each flicker imperceptible to the human eye but loaded with binary information. Data that travels through illumination, faster than radio waves, more secure, no interference. You stand in a room lit by the very signal connecting your devices. It's all one thing now, visibility and connectivity fused into photons. Historians might look back and say this was inevitable, that once we understood light carried more than just sight, once we realized it could carry knowledge, power, emotion, we would inevitably build with it, think in it, live in it. You step into a hospital room next. No harsh fluorescence, no flickering tubes, just soft, circadian-optimized illumination that supports recovery. The patient's vitals are displayed not on a monitor but projected gently into the air using volumetric light. You wave your hand and the data responds, hovering like a whisper. Light as interface, light as healer. Here's your quirky tidbit for this final stop. Engineers are now working on living light. Bioluminescent organisms genetically modified to glow brighter, live longer, and act as biosensors. Think houseplants that change color when your air quality dips, bacteria that light up in the presence of toxins, trees that glow when the soil needs water. A living, luminous language between humans and nature. Less command and control, more conversation. You find yourself walking through a park at night, not under street lamps but beneath glowing canopies. The trees themselves shimmer faintly with engineered chlorophyll, just enough to guide your steps without drowning out the stars. Above you, satellites flicker as they pass, bouncing LiDAR signals off buildings, mapping every inch of terrain in precise detail. Urban planning via real-time light scans, traffic management through light pulses. Entire cities adapting to flow, movement, mood, shaped not by concrete alone, but by illumination. And it's not just Earth. You walk into a simulation chamber for a Mars habitat. The air is dry and still, the walls lined with full-spectrum LEDs that mimic the Earth's day-night cycle. Because in the endless red of Martian dust, circadian rhythm still matters. We're learning that light doesn't just illuminate, it orients. It keeps our biology in sync. On alien worlds, light may be the most important thing we bring with us, aside from water and air. You step into a classroom of the future now, where students aren't reading from tablets but from light fields. 3D holographic projections, cast from laser arrays floating in space between desks. They spin molecules in midair, zoom through the Orion Nebula, dissect frogs with no mess. Light becomes not just content, but context. Knowledge is made of it. And there's art. Oh, there's art. You enter a gallery where nothing touches the ground. Sculptures of laser and fog dancing above visitors. Interactive installations where your movement bends light, your breath triggers color shifts. One piece just shows a single beam endlessly reflecting through a prism matrix, the angles changing with the time of day. Light has always been metaphor, but now it's medium. You think back to the first flickers on a cave wall, the oil lamps, the stained glass, the telescopes, the lasers, the quantum entanglements, the stars, the fusion cores, the glowing trees. Light has been invention, inspiration, salvation, and sometimes destruction, but it has always been forward. Now you arrive at the final door, a quiet room, minimal still. You walk in and there's nothing but a soft, pulsing glow in the center. A gentle white orb hovering, not a bulb, not a lamp, just light, formless, perfect. And for a moment you do nothing but sit. And remember that everything you've seen, every discovery, every danger, every wonder was carved from this. Photons, particles without mass, waves without medium. They define our universe but carry no volume. They heat your skin, feed your crops, charge your devices, guide your rockets, and reveal your soul. Light is what we see, but it's also how we know. And so in this final space, there are no buttons to press, no exhibits, just one request. Look around. The room is dim but glowing. You're here. You made it. And even now, the story of light is still being written.